we will see what is linear programming problem, means the formal definition, and we will try to understand what it is. Then formulation of LPP, means how do we formulate, what are the steps. Okay, those things we are going to discuss. Next, we are going to discuss about an example problem. So here I have included 3 example problems which we will discuss. From that we will get lot of confidence that okay, in this way we will convert this physical problem to LPP. And finally some practice problem I have given to you, added, so that you can uh, practice and get some confidence. Okay, so let us start with the definition. So the very basic type of optimization problem is linear programming problem, and this optimization involves modeling of physical problems to mathematical formulations into objective functions and various strategies to investigate the same. Then what does this mean, this linear programming? So minimizing or maximizing such linear functions subject to linear constraints are known as linear programming. So here you have to understand what you see. I'll put the pen on. Okay. Now you can see that the objective function, okay, it's important here. So second point, you see, maximizing or minimizing such linear functions. Such linear functions means your objective function subject to linear constraints. Okay, so when we have objective function and constraint both linear, then that is called linear programming problem. That is called linear programming. Okay, now as I have briefly introduced in last class, that we will get one objective function such as f of x. Okay, and this will be written as some constant c1 times variable x1 plus c2 times variable x2. So what I am saying, the objective function or the objective of the programming problem will be like f of x. Okay, and f of x is it will be like c1 x1 plus c2 x2 and so on. If I am taking two variable, it will be like this. So here c1 c2 are constants. Okay, a constant value like 2x1 2x3 like that, na. So 2 3 4 like that constants are there, and x1 x2 are the variable, what if you remember the field variable what we had discussed. Okay, those variables are x1 x2. Now you can see that in linear programming problem we will have this type of f of x. So here the exponent or the power of x1 is 1, power of x2 is 1, is not it? That means if the exponent is 1, if the power is 1, then that is called linear. Okay, so this function is said to be linear function. Now what about constraints? So I can write constraints as j. Okay, j 1 2 3 we can write. Okay, so if now I'm writing s1, okay, first constraint. So depending on the problem, number of constraints are there. So if the constraints are let me p1, the constant p1 x1 plus p2 x2 and some less than equal to the value d1. Okay, similarly s2 maybe we can write uh, uh, p3 x1 plus p4 x2, and here maybe x greater than equal to this d2. So this type of constants are there. Then here also you can see that the power of x1 or the exponent, okay, x square sorry x2, all the cases it will be what, 1. So these constants are also linear. If instead of x1 to the power 1, if it is 2 or 3 or any value more than 1, then that is called nonlinear. Okay, sometime we can get this type of, like, maybe p1, x1, x2, like that. If you are getting this type of constant also, then that is called nonlinear, because the exponent of x1 is 1, exponent of x2 is 1, so 1 plus 1 2. Okay, similarly for f of x also you can get somewhere like, maybe I can write g, so g of x I can write some, maybe 3x1 square x2, like that. So here 2 is a power of x1 and x, for x2 power is 1, so if we add it will be 3. So again it is non-linear. Okay, so this is called non-linear objective function. So those things are there. We will see once the course will go on, then we will see once the module will be there, where non-linear programming problems are there, we will deal. Then that time I will tell you how to do, how to solve those type of problems. So I think it is now clear that when the objective functions are linear, when the constants are linear, and when both the objective functions and constants are linear, then that time it is called linear programming problem. Now we will see a little bit or focus on what is programming and all. Okay, now in other words, we can say this linear refers to linear relationship among the variables involved in the model. Okay, model means the physical problem. So in the physical problem, when we try to write it into objective function, means when we extract from there the variables, then we will write the objective function constant. That time we can see that for linear programming problem, the relationship among the variable means x1, x2, these are the variable. So relationship among the variable will be linear. Okay, and what is the programming? So programming refers to the mathematical modeling. Okay, like from physical problem to, okay, mathematical formulation, like when a physical problem situation is given, from that we will derive this function f of x and sj. Okay, so the deriving part of the process is called mathematical modeling. For that we are writing that programming and solving of the problem that includes the use of given resources by choosing particular action to achieve the desired objective. I think now it is clear linear, what is linear, then why it is called programming. So linear programming problem. Problem means, as I have told, in and around you, whatever the situation, circumstance or system, that is called problem. So when a problem can be derived, okay, through mathematical modeling and represented in linear objective function and constraints, then that is called linear programming problem. Okay, so I hope it is now clear. So when we will deal with non-linear, that time it will be also helpful to understand and find out the difference between linear and non-linear programming problem. So next we will see there are some points. So linear programming problem or linear programming can be seen in oil refineries, chemical industries, cement industries, steel industries, mining and food. So when the concept of linear programming came into picture, after that the application of linear programming was popularized in oil refineries, chemical industries, cement industry, steel industries, mining, food processing industries, because they saw that like allocation problem, okay, like allocating some items, okay, or products, etc., etc., and then getting the profit out of the manufactured product, okay, maximization, maximum use of the machine, minimum effort. So those things are there. So direct impact was there. Okay, that's why initially that linear programming problem was introduced, was applied in this type of this industries, and further also due to the popularity and due to the wide application of linear programming problem, it is used nowadays in each and every uh, domain of science and engineering. Okay, even computer science also you can deal with that. So we will see further how to use and by taking practical or real life application problems. So next thing is that to investigate this LPP, means linear programming problem, what are the things we need that we can tell briefly. So we need to first study one of the major part in our linear programming problem is the mathematical formulation. Because you see, if you have the formula or if you have the simplified formulation, then only the calculation you can do. So that is the most important part, modeling part. So from a situation, how you will conclude a system, means how you will conclude a formula, then the formula you can use, and then after that you will get the optimum solution. So that modeling part is very important, and the modeling of any physical problem, and then different techniques to handle the same. So last one is we have to take or we have to use the technique to solve that formulation part, whatever we have done. Okay, so these are the basic steps. So next we will see the formulation part, which is the heart of the lectures, today's lecture. So the formulation of LPP can be divided into 4 steps. Okay, so first step is that we have to decide or we have to find out the decision variables. Like if we have a situation, physical problem, from that we have to derive what are the decision variables. Again, that also I have told you that it is user defined, okay, depending on the user. But we have to know how to derive that decision variable. That is the first step. So this step involves the following 3 sub-step again. What? Like each constant should be expressed in words. Then we have to see constants whether they are in greater than equal to, less than equal to, or equal form. The objective function should be expressed verbally. Identify the decision variables verbally using 1 and 2. Okay. So we will see once we are going to see the example problem, that time we will see. Next is identifying the problem data. Like each situation or each system, when we are investigating, we will find out some first we will find out some decision variables. Like for example, if I am taking a transportation problem, you are you are means going from one place to another place, then what are the things needed. Okay, so there what are the decision variables. Decision variable you can take that, okay, time consumption and cost. You are paying money for travel. So those two factors. So those two are the variable. But how those variable are dependent on the problem or situation, means what are the data involved. Like you are choosing auto, so you have to pay some money. Okay, and the number of auto availability also one option, number of bus availability, train availability, time taken by that, they are bound also. Okay, means you cannot say that okay within 1 hour I'll reach. Okay, they have certain limitation also, depending on the mode of transportation. So plenty of things are there, and that are involved uh, uh, that are involved and subjected and provided through some data. Okay, means value. So the value is very important. That you have to consider, that also you have to identify. So to formulate linear programming, we have to identify the problem data in terms of parameters. Okay, it can be in terms of parameter and constants with the decision variable. As such, the variables can be controlled, but not the data set. Okay, means if we have, I'll write, if we have like here f of this x equal to c1 x1 plus c2 x2. So this is the objective function. So in this objective function, you see uh, this c1 and c2 are constants. Okay, so these constants will not vary. Means these are the data that will not vary. Which one will vary? X1, x2. So these are the variables. Decision variable will vary. Like if time will be more, cost will be less, or cost will be more than time will be less, or either or. Okay, that may be happen. So based on that, your objective function will change. Okay, maybe five mode of transport is there, then five different f value will come. Okay, and you have to choose the optimum one, yes or no. So that is the thing. So we can say that the variables can be controlled. That's why x1 x2 can be controlled, but c1 c2 cannot be controlled. Like if you are standing at a cross and then buses are coming, so to your hometown route, maybe after 1 hour bus will come. Okay, that is not under your control. Okay, whether you will go or not, whether you will pay, that thing is under your control, but uh, the previous one is not under your control. But those data are important if you are choosing the transportation. Okay, so that's why the identification of problem data is very important. We will discuss those things through example. Next thing is that formulate the constraint. So whatever be the situation or system is there, from there we have to formulate the constraints. That is very important. So here we have to transform the verbal expressions. Whatever we have the expressions or conditions, from there we have to uh, get the constraints. Okay, transform the verbal expressions of the constraints in terms of required resources and its availability of each resource. Then each of the constraint is linear, equality or inequality. Okay, so when we write the constraints, so sometime it may be equality, like p1 x1 plus p2 x2 equal to some value, or sometime it will be p1 x1 plus p2 x2 less than some value, greater than some value, or greater than equal to, less than equal to. So that may happen. So depending on the choice, it will be depending on the constant, either it will be linear equality or inequality. So in terms of decision variable, the values of decision variable must satisfy the constant to provide an acceptable or feasible solution. You see, whatever decision variable you have taken, that must be satisfy the constraint. Okay, otherwise you will be out of the system. Understand? So if your bosses are coming after 1 hour each time, okay, if you think about half an hour, so it will be out of your reach. Okay, so you cannot frame like that the problem. So according to the constraint, you have to frame, means your decision variable must satisfy the constraint. So like if you have the value s1, I can write like p1 x1 plus p2 x2. Okay, maybe less than 100. If I am writing like less than equal to 100, so you have to choose x1 and x2 in such a way that it will be less than what? It will be 100. Okay. It will be less than 100 after putting the value. Okay, you cannot write something which will be beyond this 100. Okay, then it will not satisfy the constraint and you will not get the feasible solution. Okay, feasible solution means possible solution, layman's point of view. Just now you need to remember. In the next class we will discuss about when we will solve those problems. That time I will discuss what is feasible solution, what is infeasible solution, those things. So the last one is formulate the objective function, because depending on the objective function, okay, you will get the solution. So that is also very important part. So finally identify the objective function is to be maximized or minimized, then express the same in linear functions of decision variables. Okay, so these three are very important. Sorry, four steps are very important: decision variable, then data, constraint, and objective function. If you identify properly and formulate this thing, then your job is done. Next is your calculation part. Okay, so now we will see those four steps through example problem, how to get and how to formulate a physical problem to mathematical formula. Okay, so example 1. So read this statement of the problem carefully. So here what we have, here we have a tool and machine manufacturer produces two different type of products, that is P1 and P2. Okay, so we are getting this P1 and P2 product, this and this. Now each P1 product need 4 hours of grinding, okay, 2 hours of polishing. So to prepare the product P1 we need 4 hours of grinding, 2 hours of polishing. Whereas for P2 it requires 2 hours of grinding, 5 hours of polishing. Okay, next, the manufacturer has only 2 grinders and 3 polishers. You see here restrictions comes. We cannot go beyond that. We have only 2 grinders, 3 polishers. Okay. Each grinder works 40 hours a week. This is another limitation we have. Each grinder can work 40 hours and 2 grinders are there, means 80 hours. We can use a grinder 80 hours at max. So each polisher works 60 hours a week, means we can use 3 polisher 180 hours. So total maximum 180 hour we can use as a use the polishers, okay, per week. So next is profit on a P1 product is 30. P2 product the profit is 40 rupees. Whatever is produced in a week is sold in the market. Okay. So we don't bother about the number of products, whether it will be sold or not. Whatever will be manufactured, it will be sold. Now, how should the manufacturer allocate its production capacity to the two type of products so that maximum profit in a week can be obtained? You see, here one thing you have to remember, understand that whatever be the products produced, it will be sold. Okay, whatever manufacture, it will be sold. So we don't bother about whether it will be sold or not. We have to bother about how the production will be increased. If the production will be increased, then definitely more product means definitely more profit. But here one thing is that it's not like that if I will produce only P2 product, then I will get more profit, or only P1 product, then I will get maximum benefit. It's not like that. It may be a combination of P1 and P2. So what is that? So that is our point to understand. So what is that? how many P1 and how many P2 we will produce per week, so that we will get more profit or most profit. So that is the solution part. So first we have to formulate, then only we can solve that and get the answer. Now here you can see that carefully. From profit, we are aiming towards the profit. So profit depends on this 30 and 40 value. This we cannot change this data. So this data we can use for objective function. Now where is the restrictions are there, like 2 hours of polishing for, hello, sorry, anyone is asking anything? Okay, so 2 hours of polishing for P1 and 4 hours of grinding for P1. Those things are there. So depending on those value and those parameters, we have to formulate our constraint. Okay. Now the first thing is that what are then field variables? Sorry, what are the decision variables? So decision variable first we have to understand. Okay. Now decision variable means we have to take decision based on the production of P1 and P2 product. So P1 and P2 are the decision variables here. Okay, so we can write like this. So we can write, if x1 number of P1 product we are getting and x2 number of P2 products we are getting. Okay, means x1 P1 plus x2 P2. Okay, now this is our objective function that we have to increase. Okay. If this will be the maximum, then we will get the profit, because whatever be the maximum, that will be definitely sold and we will get the profit. But P1 is associated with what? Each P1 product, if the company is selling, then getting 30 rupees, 30 rupees profit. For each P2, they are getting 40 rupees profit. Then what will be the objective function we can write? We can write this as the objective function. So Z, I am writing it as 30x1. x1 is the number of product P1. So 30 times the number of product P1 plus 40 times the number of product P2. So that will be our objective function. Okay, so we will try to find the maximum of Z. So that is our aim. Now we will see the problem data. Now if you remember, let us see again. The problem data is there. If I concentrate on grinding, P1 is taking 4 hours of grinding. Okay, P2 is taking 2 hours of grinding, and there are 2 grinders, 40 hours each will work per week. That means we can use at max 80 hours, okay, per week, and we can use it for P1 and P2. Similarly for polishing also. So that thing we have to write and we have to formulate. Like, to produce this number of models, the total number of grinding hours. Okay, so 4 hours for P1. Okay, and we have taken, let the x1, okay, number of P1s are there. So what will be the first, then 4x1 plus 2 for P2, 2 hours for P2. Okay, so 2 into x2. So this is the first linear combination. So 4x1 plus 2x2 when we will take grinding hours. Similarly, if we take polishing hour, so first one P1 is needed 2 hour of polishing hour, P2 needed 5 hour of what? Polishing hour. So polishing hour will be used like this, 2x1 plus 5x2. But here another thing I will add is that 4x1 plus 2x2 is fine, that grinding hour, but maximum how much we can use? 2 into 40, 80 hours. Similarly, polishing hour 2x1 plus 5x2 is there, but how much you can use? 3 into 60, 180 hours. So that will give you the constant. Okay, now since the number of grinding hour available is not more than 80 and the number of possible hour is not more than 180, therefore the first constant will be 4x1 plus 2x2 less than equal to 80. Second constant will be 2x1 plus 5x2 less than 180. Okay, so these are the constants. And third one is that what? We are producing the products. So products cannot be negative, maybe 0 or positive. So what will be the then other constant? So it will be x1 greater than equal to 0, x2 greater than equal to 0. This is also called non-negative condition. Okay, so it will be there always. So whatever, even if you take number of item, number of person or things, it cannot be negative. So that's why these restrictions will be there: x1 greater than equal to 0 and x2 greater than equal to 0. So finally, if we summarize all the steps, then how it looks like? So it will maximize z equal to 30, x1 plus 40, x2. This is the objective function. Subject to these are the condition. At 4x1 plus 2x2 less than equal to 80. This is the first constant. 2x2 plus 5x2 less than 180. Second constant. Okay, then x1, x2 greater than 0. Okay. So this is the total, this is the mathematical formulation. How simplifying we are doing, you see how simplified. So from the paragraph we can derive this thing. After that, the solution part that we are going to discuss in the next class. Okay. Let us consider the second problem, little bit more complicated. You can see, okay, here we have only two variables, x1 and x2. If we have three variables, then how to do? Let us see. Okay, so here the problems will be like that, big paragraph. Okay, that will be simplified. So you have to carefully, with patience, you have to read the question. Then only you can able to write the formulation. Okay, if you understood, then it will be very easy to write the formulation. So a music company manufactures model M1, M2, M3. For example, music company manufacture like this music records. Okay, so if type 1 is M1, type 2 is M2, type 3 is M3. Okay, that have profit contribution. So you see profit is coming word means somewhere here you will get the z value, means you will get the objective function. So profit contribution per unit is 200. You see 200 rupees for M1, 450, okay, for M2, okay, then 650 is for M3. They are getting the profit from M1, M2, M3 respectively. Okay. Now the weekly minimum production requirement what? Weekly minimum production requires 50 unit for model M1, 150 units for model M2, 100 units for model M3. So weekly they are producing those things. Each type of model requires certain amount of time. Okay. For the manufacturing a component part, for assembling and for packaging. Okay, manufacturing, assembling and packaging. So three things are happening, like before it was grinding and polishing. So specially a dozen unit of the model M1 requires 4 hours of manufacturing. So M1 need 4 hours of manufacturing, 3 hours of assembling and 2 hours of packaging. Similarly, M2 needed 3 hours of this manufacturing, 4 hours of assembling, 2 hours of packaging, and like that M3 also it is given. So it will be actually M3. So M3 695. Okay. Now during the forthcoming week, the company has available 150 hours of manufacturing, 180 hours of assembling, and 55 hours of packaging. You see, these are the what deadlines, or these are the restrictions. We have to use these restrictions to construct the constraints. Okay. Now formulate this problem as a linear programming model to maximize the total profit of the company. Okay. So when there are a lot of data involved, one suggestion is that try to arrange those data in a tabular form. Okay. Then it will be easy to pick the values and write the constraint along with the objective function. Okay. Now let us move to the next step, that is formulation part. So if the paragraph is understood, then the formulation part, as I had told that tabular form, we will make the tabulation here. So M1, M2, M3. Okay. Now the production requirement is this. We had production requirement 50, 150, and 100 weekly production requirement. Okay. Now manufacturing time. Okay. For M1 we had 4, M2 3, M3 6. Okay. And total availability time. Okay. Was 150. Assembling time also we had 3 for M1, 4 for M2, 9 for M3, and 180. Okay. 180 is the assembling time total, total restriction. Now packaging time similarly 2 hours for M1, 2 hours for M2, 5 hours for M3, and we are getting, okay, 5 means 55 is the total assembling time, sorry, packaging time. And the contribution for M1 profit we are getting 200 rupees. Okay. M2 profit we are getting 450 rupees. Okay. Then M4 we are getting M3 we are getting 650 rupees. Okay. Now we will try to formulate. So the thing is that what are the decision variable here then? As we are finding how many M1, how many M2, and how many M3 we are getting, so that the profit will be maximum. So we can take X1 for the M1, X2 for M2, X3 for M3. Then we will multiply with these numbers. We will get the objective function. You see that? So let X1, X2, X3 units of model, that is M1, M2, M3, to be produced per week. Okay. And you have to find out the maximum profit. So maximum profit will be Z equal to 200 times the number of M1 plus 450 times the number of X2, because 450 we are getting profit from M2, each M2. Okay. Plus 650 into X3. Understood? So how we are finding this objective function? So objective function is done. Now we have to see the constant. So for the first constant is X1 is greater than 50. Okay. X2 is greater than equal to 150. X3 is greater than equal to 100. Means we have to uh, what? We have to produce more than 50 number of M1 product. We have to produce more than 150 number of X2 M2 product, and we have to produce more than 100 M3 product. Okay, it is there in the question. So that is one criteria. Okay, so that is the first constant you will get. Second constant is that 4x1 plus 3x2 plus 6x3 divided by 12, okay, is less than 130. 130 was the deadline, okay, or the restriction we had, no, manufacturing time. Similarly, second one, 3x1 plus 4x2. See, first is 4x1, 3x2, 6x3, okay, less than 150. It is there, okay, 130, I think. Yeah. Typo error is there, okay. Similarly, second one, 3, 4, 9, then 2, 2, 5, okay. So like that we have to do. Once we have done, the next one is number of M1, M2, M3. So we know that number of M1, M2, M3 will not be negative. These are positive value. So we can write this. Okay. Now, so this we can write it in a simplified form, like maximize z equal to this, subject to these are the constants. So 1, 2, 3, 4. 4 constants are there, and another is last one is non-negativity condition. So it will be there always when you solve linear programming problem, because objects, items, and persons, those are positive always or zero. Huh? So next one is little more complicated one. Last example problem we'll discuss. Okay. So when the complicacy will occur, there are plenty of data. Always try to make tabulation, tabular form. It will simplify your calculation, understanding. Okay. So here ABC firm makes casting where they use electric furnace to melt iron with the following specification. So what are the specifications? We will see. Material, we have two type of material, that carbon and silicon. And carbon material, okay, carbon, it will be used like from 3.20 percentage to 3.40 percentage, means we have to use that, okay, or we have to get that. Silicon 2.25% to 2.35, in between it will be there, okay. So left bound, lower bound is there, upper bound is there. Now, next we will see specification and cost of various raw materials used for this purpose are given below. Okay, so specification and cost of steel scrap, cast iron, and remelt from the foundry. So these three things are there again, because these three things, from these three things we will get the carbon and all. So steel scrap, carbon percentage is 0.4 and silicon percentage is 0.15. And the cost is what? 1030 per ton. Ton means 1000 kg. Okay, those units you should understand. Okay, cast iron, carbon percentage 3.8%, silicon percentage 2.4%. Okay, then remelt from foundry 3.5% carbon, 2.3% carbon, and their corresponding cost is given per ton. So if here it is very important to understand, if the total charge of iron metal required 4 tons, total charge of iron metal, total charge of iron metal means steel scrap, iron, means cast iron, remelt from foundry, total, okay, metal required 4 ton, we need 4 ton. Find the weight in kg of each raw material that must be used in the optimal mix at minimum cost. Okay, so this material will be mixed. Okay. So we will see. Okay, first it is asking in kg. So 1 ton means 1000 kg. First that we have to convert. Okay, then how we will proceed, we have to see. You see, somewhere it is given, first table you can see minimum and maximum. So this minimum maximum will be helpful to construct the constants. Okay, now what we are doing, x1 x2, we are taking this as x1 x2 x3 be the amounts in kg of the raw materials, like iron scrap, steel scrap, and foundry, melting from foundry. Okay, the objective is to minimize the cost. Okay, we have to minimize the cost. So for first one was what, 1030 per ton. Okay, but we are finding in kg, that's why you have to convert it into kg. So 1030 by 1000 x1 plus x2, if the second material, that is steel scrap, that is 1100, we are getting profit, so 1100 by 1000 x2 plus third one is 850 by 1000 x3. So this will be your minimize, means the objective function that we have to minimize. Understand? Now for iron melt, first one is iron melt. Okay, that we have to see from iron scrap or iron melt, whatever we had. So for iron melt to have a minimum of 3.2 carbon. So 3.2% carbon, what are the means how we'll write? So zero point 0.4 you can see here, 0.4 percentage carbon. Okay, for this material 1, material 2 3.8% carbon, and for material 3 here 3.5% carbon is there. Okay, but again carbon is divided minimum and maximum. Okay, so minimum, the percentage of carbon should be there in the mix is 3.2. So how we will write? So 0.4 x1 plus 3.80 x2 plus 3.50 x3, okay, should be greater than 3.20, because this is a minimum value. Above that it is possible, but not beyond this 3.4. That's why it is written like this: 0.4 x1 plus 3.8 x2 plus 3.5 x3 is greater than equal to 3.2. 4 ton, but we are dealing with 4 ton. 4 ton is 4000, so that's why we have multiplied 4000 here. 3.2 into 4000. Similarly, iron melt to have a maximum is 3.4% carbon is maximum, means below that is possible. That's why the combination this 0.4 x1 plus 3.8 x2 plus 3.5 x3 should be less than equal to 3.4 into 4000. Clear? Similarly, you can find out for silicon also. Silicon minimum is 2.25, maximum is 2.35. Okay, and the values are like this: 0.15, 2.4, 2.30. So 0.15 x1 plus 2.4 x2 plus 2.3 x3, that will be the linear combination. Then we have to see the bound, minimum, maximum. Minimum is less, greater than 2.25 into 4000 you have to do. Maximum is less than 2.35 into 4000 you have to do. Like that we have done here. You see this 2.5 and 2.6 constant. So like that we can get 4 constants. Okay. Third one is that here I have underlined total charge of iron metal required is 4 ton. Means if you add these things x1, x2, x3. So x1, x2 means x1 plus x2 plus x3 is 4000. This is another constant. So you see, you can see that this equality sign is there. So that is called equal constant, equality constant. Here inequality sign are there, greater than equal to, no, less than equal. That is why it is called inequality constants. Okay, so it is a mixture of all. In this problem we will have mixture of all type of constants, and finally whatever be the x1, x2, x3, that will be positive or 0. Okay, non-negative value. So this is what the final formulation, like minimize z equal to this, subject to these 5 constants along with the non-negativity condition. Okay, so in this way we can formulate. I hope you get some idea how to formulate the physical problem to mathematical formula. Okay, in the next class we will see there are some methods. From this point onwards we will see how to find out the exact x1, x2, x3 or x1, x2, x3 approximately whatever what will be the value, so that we'll get optimum solution. Okay, so this is the final form. You see how nice it is looking like. So from the complicated paragraph we derived, this is the objective function, and these are the constants. Okay, x1, x2, x3 are the field variables or decision variable, you can say. Okay, so next I have added two problems. Okay, for you can practice, you can do your own. Okay, so this is what we had for today's class. Okay.